Right, welcome back to Periodicity, this time in part 2, and today we're going to be looking at the melting points and to some extent the boiling points of the period 3 elements and how they vary across the period and how we can explain them. So last time out in part 1 we looked at general structure of the periodic table and refreshed some of the terms there back from GCSE. So today what we're going to be looking at is the bit underlined down here where we're going to be looking at the melting points and boiling points of sodium to argon. Okay, so as a quick sort of look at this, so we're focusing on period 3 here, and we're moving across from sodium to magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. So we need to think about how we're transitioning here from our metals on our left, so sodium, magnesium, and aluminium. Then we're hitting silicon there, which is a semi-metal, so the properties have changed there. It's got some properties of a metal, some of a non-metal, and then phosphorus, sulfur, and chlorine, they're simple molecules, and argon is a noble gas at the far end. And we're going to link the idea of how these are bonded together to explain our melting points. So here's a load of data that we've got on here, again showing that our sodium and magnesium here and aluminium, these are all metallic. Our silicon is a giant covalent molecule. Molecular or simple covalent, I've described the phosphorus, silicon, sulfur and chlorine, I beg your pardon. And then finally argon, it's a noble gas, it doesn't form molecules and it exists as simple atoms. Okay, so we've described its bonding as just being atomic. Now I've included down here the formula of the common elemental forms of phosphorus, sulfur and chlorine, and these are the ones that you might typically see. Some of these do have other forms that exist, but these are the ones that we will be looking at. And then I've got my melting point and boiling point data. So here's a graph showing them. So I'm going to focus initially on the metals down here, sodium, magnesium and aluminium. And we can see that the general trend of those is that our both melting points and boiling points are going up, so they're increasing. So what we need to think about is to help try and explain why. So our melting points and boiling points both increase, and it's metallic bonding. So if we remember what metallic bonding is, this is when we would have a lattice of ions. So I'll just put some positive ions in the middle there. Apologies for my pen, it's not very good. And around these, what we would get are our delocalized sea of electrons, and it's the electrostatic forces that are holding this lattice together, this attraction between the positive and the negative electrons, positive ions and the negative electrons. Now, as we move between these, we've got sodium and magnesium. If we look at the magnesium, for example, I'll just erase all on here and start again. So let's say I've got my sodium, and I'll just do a very simple lattice here. So they're positive, and with negative electrons delocalized around it. I then compare my magnesium, which has got 2 positive ions, and twice as many electrons delocalized around. So this time I've got a bigger ion, bigger charge on my ion, on what is probably a smaller overall ion size of this metal ion in here. So I've got a greater electrostatic difference between my electrons and my ions. So if there's a greater difference between our positive and negative ions, we've got greater electrostatic forces, so therefore they're held together more tightly and require more energy to overcome, which is why as we move from a sodium, magnesium, aluminium, when the valence electrons are delocalized, leaving behind those little metal ion centers in our lattice, then we get greater forces of attraction between the metal ions in the center and the delocalized electrons, and therefore higher melting points as we move across. Okay, so silicon, I've just sort of highlighted it here in the middle. So silicon has also got much higher melting point even than any of the metals, and we've got to use our understanding of structure and bonding to explain why. Well, silicon, if we remember, is a giant covalent molecule, so this will have many strong covalent bonds holding this giant covalent lattice together, and therefore a lot of energy is going to be needed to overcome all those covalent bonds. Okay, so the final section, so we're just on the running down here, so we can see all of a sudden at phosphorus the melting points and the boiling points drop right down. Okay, so these are much lower again compared to the silicon that they've just that's preceded it. So now we're focusing on this region here. So it's a bit of variation, but we can see phosphorus to sulfur, then down to chlorine, and then down to argon. Okay, so these values are in Kelvin, by the way. So chlorine and argon, you can see they're going to be gases at room temperature, which we know. And now we're just looking at the size of these individual molecules. So sulfur of these has got the highest melting point of 392, and it's the biggest molecule. So now we can start bringing in the idea of our intermolecular forces, and particularly the van der Waals between these. Because argon is a simple atom, it doesn't really have intermolecular forces as such, but you will still get van der Waals interactions between them as the electrons are distorted around the atoms. So, what have we talked about? Well, we've described the trends in melting point across period 3. So we've looked at how the metals, they've increased, how silicon has a much higher melting point than the others because of its structure, and then also how the smaller molecules and the atoms change as well. And we've explained this trend in terms of the bonding, going from metallic to giant covalent to simple molecular to atomic, and talked about the forces that are holding these together. So what is it that holds, or what forces of attraction are there between chlorine molecules, between argon atoms, between the atoms in a sodium metallic lattice? Okay, in part 3 we will be looking at some other properties that we've got in there, including atomic radius and things like that. Okay, thank you for watching. Goodbye.